Now some people can't tell the difference between my i's and j's. My i's at the bottom will curl off to the right, my j's curl off to the left. Vector math problem. Let's see if this makes any sense. If that answer makes any sense, because there's another way of adding vectors. This is the way we did it here is the way you would add vectors if you wanted a precise answer. If you just need a general ballpark, we can add them graphically. All right, so if I'm going to add them graphically, this is known as the head-to-tail method, although calling it tail-to-head probably would make more sense, but head-to-tail is the way it's called, the head-to-tail method. Vectors have a magnitude and direction, so I just create a point and pick up slightly more space there. And what I'm going to do is I'm going to draw a vector that represents 5 meters and 37 degrees. Well, 37 says 45, 37 somewhere around in this direction. And I'm going to say that's 5 meters. So all I've done is just draw it, and I try to draw it as accurately as I can. This is just a crude sketch. If I wanted to do it really precisely, I'd pull out a protractor and a ruler and come up with a set scale. But I'm just trying to see if this answer makes any sense at all. Now I'm going to do that. For the vector, my symbol here, this is the tail, that is the head. Think of an arrowhead, got a sharp point on it. This is the head. My second vector, I'm going to start here. This is my starting point for the second vector, and I'm going to go at 60 degrees, which is roughly somewhere in this direction. And the length is 4. Well, if that's 5, 4 has got to be shorter than that, probably about that long. Somewhere around there. And so the answer is a vector from where you began to where you ended. I started here, I ended there. Wow. That blue arrow, this is A and B, this is A plus B. Well, I went to the right and I went up, so that part matches. Just crudely, say I went to the right that far, I went up just a little bit farther. So up is a little bit more than to the right. Ballpark, this seems reasonable given my drawing.
And so when you're drawing it, you assume you start at the end of the first vector?
Mm-hmm. That's the head to tail. That the head of the first one is this place where the tail of the second one is. The order does not matter. The commutative property of addition holds, and so I could have drawn B first and then drawn A, and I should end up in the exact same spot. If you've had conceptual physics, Hewitt talks about the parallelogram method. This one's slightly more versatile as long as if you deal with more than 2 vectors. Parallelogram method is a nuisance. If you don't know what the parallelogram method is, don't worry about it. It is not the method that you wish to use. Okay. Now notice I started in polar form, I ended in rectangular form. If I don't specify, there's absolutely nothing wrong with that. If I don't specify the final form. However, just for the fun of it, let's figure out what is the answer in polar form. So let's say I'm going 5 meters, I hat is to the right, so I'm going 6 meters. And then I go up the j-hat direction, 6.46 meters. And they are perpendicular to each other. My answer is from where I begin to where I end. That's my resultant, and this is the time that I use the double print. R for resultant, that's resultant is just sum of vectors. So first, let's figure out the magnitude. It's a vector. My answer is a vector, so I need a magnitude and a direction. Magnitude is the simpler of the two, so let's do it. How would I find the magnitude of R?
Which is vector.
Yes. So 6 squared plus 6.46 squared is equal to R squared. Now, just from a notation point of view, I've got this vector squared. What does it mean to square a vector? As we'll get to later on, it's a vector doing a dot product with itself. Basically, it's just the magnitude squared. So I could write this also as just R squared. Dot product, just sort of tuck that away in the back of your head for the moment, and when we get to it in chapter 7, I think, you'll go, oh yeah, I remember, we talked about that. So it's the magnitude of the resultant. Oh, also for magnitude of the resultant, I could also have written the magnitude of the resultant as just putting absolute value marks around it. And just because physicists are an arrogant bunch and they all want their own notation, some textbooks will also write it with 2 sets of absolute value marks around it to differentiate it from absolute value.
What I got was 8.81646187538.
All right, let's just go 2 decimal places, just for now.
8.81. Oh no, 8.82. Sorry.
And then let's finish it off. These are in meters, so this better be in meters. So my magnitude here is 8.82. Well, if these were in the same direction, if that and that were in the same direction, it would be 9 meters. It's going to be a little bit shorter than that. That makes some sense. Now I need to find the angle. I need to find this angle. I could find the other one, but in order to determine the direction, this is the one I want. Angles are relative to 0 degrees. And that's 0 degrees. Positive angles go this way. Well, I have 3 sides here. This is 8.82 meters. I got 3 trig functions that my calculator can do. So we pick one. I know that the tangent of theta is equal to 6.46 meters over 6 meters. Meters cancel out. That's not right. That might be right. So theta would be the arctan of 1.076 ridiculous, and that's not a careless error. Someone's about to.
That was good.
Now, actually, before we come up with an answer, let's come up with some at least reasonable number here. I know I go that these two are roughly the same. Very crudely, rounded off, they're the same. So that if they were the same, what would the angle be? If I go to the right and up the same amount.
You want 8?
Sorry?
90 degrees? I think it goes just
90 degrees would be straight up when I'm done. If I have a triangle where the 2 sides, these 2 sides are,
45.
yeah. So 45 degrees if they were the same. I'm going up a little bit more than I'm going to the right, so it should be slightly more than 45 degrees.
So 47 degrees.
Something like that. All right, so did you crank through the math, and anybody tell me what? First off, is that correct?
Yeah.
Okay, and this one?
47.1 meters, or not meters.
Not meters.
Not meters.
You're correct, it is not meters. I don't want to feel like writing down not meters. That doesn't narrow it down quite enough.
Degrees.
Degrees. It's an angle.
Look, 41.
So, and that comes out pretty darn close to what we sort of speculated the angle should be. The advantage of the graphing method is it gives you a quick and dirty to go, yeah, that answer that's close enough. If we had done the other ones, if I had done the theta is the arc cosine of adjacent over, so 6 over 8.82, or theta is the arc sine of opposite over hypotenuse, so that's 6.46 over 8.82. I take it out, if somebody could give me these out to 2 decimal places. I believe there's gonna be a slight difference here, at least for what I want to talk about. I think there is. It should be somewhere around there. If you get a crazy different answer, then you might want to check radians degrees. Actually, if you were radians, you would still get similar answers. So what was this one?
47.14 degrees.
All right. So I have 3 different answers here. On a quiz or a test, I probably would not notice that the difference, that's going to be close enough. I think there's been only one test where I wrote the problem wrong, but it was possible to skip something and get an answer really close to the correct answer. So I had to watch out for that. But usually I'm looking at that and going, okay, good. I quickly move on. On the lab, I would go through the calculations to see how you got that. On a quiz or test, any of those are correct. However, one of these actually is more correct than the others. Which one is the most correct of the 3? And why? Would be another part of it.
Well, would it be the tangent function because we probably rounded the 8.82?
Yes. Even though the 6.46 has rounding in it, this is based upon that. This has an extra level of rounding. So that indeed, tangent is indeed the more accurate of the 3. Or I guess with 3 of them, the most accurate. So if you're designing a building, well, take it out more decimal places, but go with this one. Questions? All right, so let's do something official here. Class is not over, and even though this stuff is, I think it's included in chapter 1, maybe it is. The chapter 1 homework, if you go on the Blackboard, assuming you've done the course entry assignment, and then click on coursework, then click on chapter 1. At some point you will see technical homework problems. A week from today, we're gonna have a quiz on. What's gonna happen is I am going to pick 2 of the problems, change the numbers, present that to you as a quiz.
So you have a 50-50 shot at getting that.
How do you get 50-50 shot on that?
I know, you have like, if you get one wrong, it's 50, or is that not?
Oh, the way I do grading, my philosophy on the grading is that if I gave you, it's a 2-question quiz, if I gave it to you as 2 1-question quizzes, and you got 1 right, 1 wrong, that would be an A and an F, which to me averages out to a C, as opposed to 100 and a 0, which averages out to a 50. My grading system is designed so that if you're having a really bad day, it's not gonna keep you from getting an A and it won't keep you from getting an F. It'll help slightly towards getting an F, but no one grade is going to make or break you.
Yeah.
So it's a generous grading system. I take off for really little stuff, but if I had to crudely estimate it, it's like a 20-point grading scale. If that disturbs you and you want to use the school's 10-point grading scale, let me know in front of witnesses, and I will be glad to do that for you. I did have a student once who wanted it. The other student said, no, you don't want that. That student had other issues. Sorry, flashbacks, not good ones. All right, so there should be a link underneath the textbook problems that says if you need help with it or hints or something like that, you click on the link, or you go to supplemental material, textbook homework, solutions or help or something like that. The solutions are written out.
Is that something that we turn in a blackboard or do you?
No, the homework, it is there for you to study to see if you understand the material and prepare for the quiz. If you like surprises, you don't have to do them at all. I did have a student a number of years ago. I don't think he ever opened up the textbook. He always took an incredibly long time, to the point of taking quizzes. At some point I'd say, why don't you step out in the hallway and finish? And then we'd just start class. He ended up with an A. But he could have been a whole lot faster, I think, if he had actually looked at it beforehand. All right, any questions about the quiz a week from today?
And it's just on chapter 1, right?
Yep. And it will be the problems that are assigned. It will be from the problems that are assigned. In chapter 2, there's something called master sets. That is something that will be handed in on paper or submitted online.
So is this how all your quizzes are gonna be like? Is it gonna be based off of homework or?
The in-class quizzes, yes.
Okay.
There are going to be a slew of quiz grades, so if you have a bad day, just relax, do better next time. All right, chapter 2. This actually, I think, falls into chapter 2, but we need something more specific here. We're going to do everybody's favorite part of class, vocabulary. Woo! Because there are certain key words that you need to recognize. Because some words automatically are vectors. And so you need to use vector math. And some things are automatically scalars. In which case you do the regular math. First, vector term, position. Now the symbol that I use for position, there's a number of them, R, S, X, Y, Z. These are the most common ones that are used. I tend to use X a whole lot. Some textbooks are more stringent. They'll use X for anything horizontal, Y for anything vertical. R, basically, we use R more often when we're dealing things which have some radial symmetry. And S comes from the Latin word stadia, which was basically their mile, the ancient Roman mile. So position is just where an object is. With respect to the origin. So if I'm asking for the position of an object, I am asking for a vector.
Also on like a problem or a question, it would say position of something, and then you'll know the vector.
Yes. All right. Another vector term, displacement. Now, there's also a displacement dealing with, I have a beaker of water, I put something in it, the water displaces. It is related to it, but not a whole lot, or not as directly. Displacement has basically two definitions. Where an object is with respect to the starting point. Or change in position. So the symbol used for displacement is basically whatever you're using for position with a change symbol in front of it, and change is represented by the Greek letter delta. So delta R, delta S, etc.
So when you say where an object is with respect to the origin versus where an object is with respect to the starting point.
So let's say I have a coordinate system right here, that's my origin, and I have an object there. That is the initial position. I'll use X sub I for initial. I then move to here. So this is my final position, X sub F. My displacement is where I am relative to where I started, or the difference between these two position vectors. That's my displacement right there. My displacement is that way, my final position is that way.
Okay.